Hey, hey, are you in there? Are you where? No, no. Okay. All right, I'm gonna do lesson 78, solving quadratic equations, part 2, the sequel to end all sequels. I was thinking, when in the world did we do that? I don't remember that, so I looked it up. Lesson 35 was part 1. So finally, you've been waiting. You've been waiting and waiting since the second quarter to do this one. And of course, the part that I want to show you is like hard to see. Oh, man, using the difference of two squares. Pretty much every problem we got today in some way is going to involve the difference of two squares. So I want you to look for it. It's one of my favorite ones, and this is part of the reason why. It's a great factoring form. I used it in the proof for Heron's theorem, Heron's rule for the area of those triangles. Remember those? I had to use it. So I was like, oh, wait, that's the difference of two squares. I can factor it. Yay! And our goal of factoring here is going to be so we can solve the quadratic. We can get solutions. We can find zeros. I know we know like 4 ways to do this, okay? But today, no calculators, no graphs, just straight up algebra. Let's math this sucker. Difference of two squares. For review, a squared minus b squared can be factored down to a plus b and a minus b. Let's get a little more complicated because that a can be just one number or a variable, or it can even be power of a variable, like x squared, or it can be a polynomial in itself that's being squared. If we can find out that there's 2 of them, right? If we can find out that there was something times itself, again, like a 2x minus 3 squared minus 3x plus 1 squared. And then we can split that up into a plus b, a minus b. Eventually, what we're doing here is setting this equal to 0 so that we can eventually solve for x, or solve for whatever the unknown is. So I've got here a few examples, and we're going to keep ratcheting up the intensity until we get to the hardest problem here at the end. First one's not too bad. I could draw a picture with that one, right? I could think it through, and I'd be like, okay, well, 9x squared, and then there's nothings, and then there's a negative 25. Maybe I can't draw a picture. No, yeah, I can. No, I can't. No, I can't. Well, at least the hard part is not splitting this up and writing it like this, because I can see that 9's a perfect squared, and x is squared, and that 25 is a perfect square as well. So this side turns into 3x plus 5, 3x minus 5 equals 0. And then using the zero product property, we can set each of those equal to 0 and solve. In this case here, x is negative 5/3, and in this case here, x is positive 5/3. There's our 2 answers. We know it has 2 answers because it's a squared thing. Thus says the fundamental theorem of algebra. Right, that's the easy one. Now we get to a little bit harder one. We're like, wait, 7 is not a perfect square. That's okay. If we rearrange this to make it equals 0, we have 7x squared minus 63. And we see that 7 is a factor of both 7x squared and 63. So that's what's left, right? And we can discount that 7 because 7 will never equal 0. The original expression is equivalent to the expression, or at least has the same solutions as the expression x squared minus 9. So we've got 7 And then we've got inside of that, we've got x squared minus 3 squared. The difference of two squares. So we got our 7 hanging out there, and then we've got x plus 3, x minus 3 equals 0. X plus 3 equals 0. X minus 3 equals 0. So x is either negative 3 or x is positive 3. There's our two answers. All right. Remember, hit pause if you need. That's just a smidge harder. We had to do one extra step, maybe two extra steps. What about cubics? What about it, yo? Can we make those into using the difference of two squares? Can we take that tool out of our tool bag? Well, I'll move this one up here. 10x cubed minus 10x. We see that both of them have a 10 and an x in there. We factor out the 10 and the x, and we're left with x squared minus 1. Oh, we failed. Oh, no, we didn't, because 1 is a perfect square. So this factors down to 10x, x plus 1, x minus 1. It's cubic, so we've got to have three answers. We see that 10x can equal 0, x plus 1 could equal 0, or x minus 1 could equal 0. So x equals 0, negative 1, or positive 1. Now, the next one that I'm going to do is a little nuanced. That's French for tricky. But it's not too bad. It's quartic, and there's no squared part here. So I'm going to play a game that you're going to see more often the further on in math you go. If you get something that's kind of complicated, you basically put it in a simpler form, right? And then you work with the simpler form, and then you put the complicated part back in when everything's all spread out. That is, I'm going to use substitution. And in math world, oftentimes when we use substitution, we're going to use the letter u. And here I'm going to let u equal x squared. Okay, so I got to rewrite this thing. X to the 4th minus 16 equals 0. If u is equal to x squared, then x to the 4th can be rewritten as u squared minus 16. I will take this and hold on to it for now, and I'll put it back in the equation later, but now I have the difference of two squares. So I can split this up into u plus 4, u minus 4 equals 0, right? Because this is 4 squared. Yes. Now, I'm going to put that thing back in for u. That means I'm going to put the x squared back in. And you notice that here I have the difference, or sorry, the sum of two squares, which I can't really do anything about. It's going to give me some complex roots. And I've got this, which is the difference of two squares again. So I've got x squared plus 4, and then I've got the difference of two squares of x plus 2, x minus 2. I'm still going to have 4 answers. 2 are going to be complex conjugates, and I'm going to have to answer negative 2, and I'm going to have positive 2. X equals negative 2, x equals positive 2, and then we're trying to solve this little problem right there. So x squared equals negative 4, x equals plus or minus 2i. 1, 2, 3, 4. It's quartic. There's 4 answers that I have to have. Plus 2i, minus 2i, negative 2, positive 2. If you multiplied all those things back in together as factors, you would end up back at x to the 4th minus 16. That's pretty clever, isn't it? I really like this. If I can recognize this as the form for the difference of two squares, it's like, wait, I can do this. I realize x squared squared. And then take that thing that's, equal to a here, or I made it u, and simplify it a little bit, and then put it back in when it's easier to deal with it. That's pretty cool, huh? I kind of like that. That'll even work if you got a quartic that's like this. Yeah. Even if there was another piece in there, I could have substituted and then moved forward. Last one. And this is that they've had to have contrived this thing. They had to have really thought hard about how they're going to write this one to make it work. Let me just tell you. There is our problem. We're taking a polynomial minus another polynomial, and we want to solve this thing. We want to figure out what this would be. So if you're looking at that just on face value, you might start thinking, well, I'm going to do some math, right? I'm going to go 9x squared minus x squared, get 8x squared, and then I'm going to go negative 12x minus 10x, and 4 minus 25. I can't factor that. And then you maybe punt and you do the quadratic equation. But no, we need to use the difference of two squares. That's what we need to do. So, I mean, you could do this, and you would get the right answers, the right solutions eventually, but we're trying to use a different tool here, and they wrote this problem for us to use our difference of two squares tool on. All right, that'll still work, but let's do this. Let's take this one here, 9x squared plus 12x minus 12x plus 4, and we'll do the clumping and splitting business over here to see what is being squared. Okay, 9 and 4 is 36. 36 breaks down into, I can do negative 6 and negative 6. How about that? How's that sound? Sounds pretty good. So we're going to rewrite this as 9x squared minus 6x minus 6x plus 4. I can kind of see this if I was drawing this as a big old square, right? What could I have done here? 9x squared came from 3x and 3x. And then we could have split up this into two equal parts, and that would mean that we'd have a minus 2. And then that's where our plus 4 came from. So this turns into 3x minus 2 times 3x minus 2, or 3x minus 2 squared. All right, we found it. Found a perfect square. And then we got minus, and then we got this one right down here, which is a little easier to work out because we got a perfect square there at the end. And we've got twice of x times 5 right there. So this one turns into x plus 5 squared. A squared minus b squared. You see it? The difference of two squares says that we can go 3x minus 2, a squared, a plus b. A plus b, b plus b, a plus b, and a minus b. 3x minus 2 minus x plus 5. Okay, so this is pretty easy math inside here. Oh, equals 0. Equals 0. 3x plus x is 4x. Negative 2 plus 5 is a plus 3. This one right here, 3x minus x is 2x. Negative 2 minus 5 is negative 7. There's our two things that we need to set equal to 0. And this one turns into x's minus 3, negative 3/4. This one right here turns into x equals 7 over 2. Now, actually, I think that this one, quadratic equation would give you that. Those are okay numbers, but this was actually kind of fun. And like I said, didn't have to use a calculator for any of this. I could just use my brain, and I'm looking for structure. I'm looking for the difference of two squares as being the tool that fits my particular problem. Okay, that's your lesson for today. Try to keep it concise. You're going to be getting that to me at some point, and then we're moving on